Hi, so hope you are all set to also to discuss a little more about frontal numbers, right? So where we stopped was that we were discussing what's the effect of very small frontal numbers, okay, and so yeah, what does a very small frontal number mean? Which is a picture like something like this, right? Where this is actually for a very large frontal number, where the thermal boundary layer thickness is like very small compared to the velocity boundary layer thickness. And we then looked at a little bit of the math, what we can do. So we looked at frontal number very small, right, and we looked at the math and what kind of simplifications it brings about. And we saw that we could actually write the frontal number, the Nusselt number for a large frontal number in this fashion, right? And hence, you come up with equations, simple, formulae which one can actually use from this consideration. So that's that. So now the next thing to do is to basically be looking at the two the limiting cases. So this was, we discussed about when the frontal number is very small, and so where the thermal boundary layer, we discussed this, the thermal boundary layer is much higher, is much large, right, compared to the velocity boundary layer thickness. So what we're going to discuss now is about this, when the frontal boundary layer, when the frontal number is very large, which means that the thermal boundary layer thickness is very small. Okay, so let us sort of do that now. Okay, so we will go and discuss this. So let us see. Okay, so we're going to talk about that. So we're going to talk about large frontal numbers. Okay, now so large frontal numbers, that. Okay, now this was actually this problem was first okay, I'm actually not even going to try and pronounce that. So this scientist basically, and right, so the thermal boundary layer thickness is much smaller than the velocity. So basically the velocity boundary layer thickness is the one which dominates. Okay, so in other words, we can really say that the entire thermal, because this because this thing, this thermal boundary layer thickness, because this lies, this is very small. It is really very small compared to the velocity boundary layer. So we can basically say, right, we can basically say that the entire thermal boundary layer, right, lies within that region, right, where the velocity depends velocity is a function of y. So, let us just go back and look at this diagram right here. Okay, now these are the two cases. Now, if you say this was the frontal number very small case, right? This is the one that I'm talking about here. This is the one that we looked at earlier. So this is where the Prandtl number is very small, right? And you can see that here the thermal boundary layer is large, right? It's large, so it spreads from the surface to about this height, right? But for the majority of this distance, right? For the majority of the distance, which is like from here to here actually, okay, the velocity is constant. The velocity actually is v infinity, isn't it? Because this is delta x, because delta x is the boundary layer thickness, right, the velocity boundary layer. So that really goes up there, and after that the velocity remains constant. So therefore this is the u, and this is the this is the u, right? So that's what we're talking about right now, that here delta th, right, for the case that we're considering now, which is for very large Prandtl number, right, the delta th is the thermal boundary layer thickness. A thermal boundary layer thickness is just this small, right, just this much, right? But since the velocity boundary layer is very large, now that extends from here to this much, right? This is the entire delta, but delta th is just this much. So what basically you can see that the thermal boundary layer actually overlaps, right, the delta, in the sense that here there is a difference in the temperature, right? So you go from the wall temperature to this, right? And the velocity also goes from, or some temperature, so I can say that, or say u. Let me call that as u, and here u is 0. Okay, let me write that properly. So basically what I'm saying is here u is 0 and here it is uy. So you have both, right? Unlike in this case where, so that is kind of different from what we did earlier. So that's what I mean actually when I say this. Okay, depends on why. So if we then can write the velocity components close to the wall, so we can write this, okay, we will write the velocity components close to the wall. So we can write that okay. Okay, so if we write the velocity profile, velocity description, like this, then the energy equation, which, okay, I will just write it again here. So the energy equation, okay, this can be basically, this is basically, it can be reduced, right, to an ODE, which is an ordinary differential equation. So this is a PDE, right? So partial differential equation. So we can reduce this to an ordinary differential equation using a similarity transformation. So if I use these velocity, if I use this description for the velocity components close to the wall, then the energy equation can be reduced to an ODE, right, using a similarity variable or transformation, similarity transformation or variable or whatever it is. Okay, so let me write that. So what is that similarity? variable. So what is that similarity variable? Now that similarity variable can be written as y okay 9a x tau wx right, where I hopefully you remember what the x naught is. X naught was the location of the temperature jump. Let me just go back and show you, just remind you of that, right? So if you took a if you took a flat plate, so this x naught was the location at where we had this temperature jump. So we basically then again, the integral is basically from x naught to x, right? Now, so if we use, so this is x actually, okay. Now, so if you use this similarity variable, okay, then my energy equation reduces to, so therefore using basically what I can say is that, so if I use this, right, right, and then what I get is this, then the energy equation becomes d2t dA to 2 okay. So now, well, basically this is getting a little mathematical, so I will try to keep it simple, okay, because it is it would be nice if we had enough math background, but that's okay. If the progress in fluid mechanics has always been related to the development in math, and the mathematical progress is so important, because if we just come up with all sorts of weird equations, and then we have to sit and solve them. So, I mean, we have to be grateful to the mathematicians, right, to help us do these things. So the entire numerical methods, etc., would have never, seen much daylight without the contribution from mathematicians. So, not that I understand all of it, but I will try to keep it brief and give you just a little overview as to what we do here. Okay. Now this is a standard, so this has a solution, this has a solution which is for, in terms of an incomplete gamma function. Okay. I will explain briefly about that. Let me first write the solution for you, right. So if I have this, right, so then so this equation can be solved, okay. This equation is solved, and what you get from there is this is the solution, okay. Okay, L rho by, okay, tau W okay, and so I mean, so this is basically the solution, okay, and here, so this 0.5384, right, so this 0.5384 this term, right, so this thing is basically okay, by this, right? Now, so therefore, this gamma, the capital gamma that you see, this is nothing but the gamma function, okay? So what I will do is, so this is basically the solution. Okay, now this is basically the solution that you get. So, so the whole gist here is that for large Prandtl numbers, if you use this velocity components description close to the wall, then the energy equation is reduced to an ODE using this similarity variable. So the equation becomes this, and this has a standard solution in terms of the incomplete gamma function. And so let me just sort of write down, okay. So this has a solution in terms of the incomplete gamma function. Right? Okay, so let me just tell you what exactly is this gamma function. I'll do this very briefly. Okay, so now the gamma function is, so what is exactly a gamma function? Now, gamma function, gamma n, is nothing but n minus 1 factorial, right? So basically, it's similar to the factorial, except it is like n minus 1. Factorial n would be factorial n. So gamma n means 1 less, than n factorial. Now, let me sort of explain on what do you mean by the incomplete gamma function or something. Okay, now for complex numbers, okay, with a positive real part, okay, it is defined via an improper integral. Now, what exactly is an improper integral? So anyway, let me sort of write this down. Now, for complex numbers, okay, with, this is important, a positive real part, okay, a positive real part, right, it is defined via an improper integral, okay, which looks like this. So that is gamma t, right, is equal to right, where this t is basically a complex number, right. So t is a complex number, with positive real part, right, which is that real part of t is greater than 0. Okay, and well, gamma function is basically defined for all complex numbers except negative integers. Okay, so okay, I can write that as well. Okay, I can write that as well. So let's just say gamma functions are defined well, for all, let's start do that, okay? For all complex numbers except for negative integers. Okay, got that? So, and what is nice is that this, this basically this is an integral. Okay, so in terms of the gamma, so we said gamma 1 by 3, as you can see, it's a positive number. So now this basically this converges, right, absolutely to the what is called Euler integral of the second kind. Okay, now then if we use sort of integration by parts, when we use integration by parts, what we can, using integration by parts, what we can say is, okay, this, right? Now along this, if I combine, gamma of 1 is 1, right? Then what we can write is gamma of n is basically 1 into 2 into n minus 1. So which is nothing but n minus 1 factorial. So again we can also write gamma t is gamma t plus 1 by t. Okay, so this is a little bit about gamma function. Now what we said something about improper integral. It is defined via an improper integral. What exactly is now an improper integral? Okay, let's just define that a little bit. Now improper integral, basically the limits are, it's actually unbounded. So the limits are infinity, so let me give you an examples for that. So improper, so improper integral, okay, so the limits, okay, if I give you examples you will find it better. Limits of integration, okay, are either real numbers, right, or very large or very small. What I mean by that, for example, if I give you the examples, for example, say we have limit, okay, so we have functions like this, say p1 to p2 fx dx, okay, then we'll have function, we'll write this again. Again, p1 to p2 fx dx. Now here, so I can say limit, for example, p2 tends to infinity, right? Or I can say limit p1 tends to negative, right? Negative infinity. So basically what we're saying is, it's an unbounded domain. This is basically an unbounded domain. Okay, so now, well, I can explain that a little bit. You can kind of understand that. You could have, say, some, I don't know, some function. So say this is your, x and y or something. Okay, so this is y in the sense this is actually your fx. Okay, this is your fx. Y is equal to fx, right? So p1 is some boundary. Okay, so p1 here is some boundary. This is, say, this one, but p2 is infinity, right? So say I have this function, so this function is something like this, something like that. So then, if I had to integrate this, right? So all I do is basically take the area under the curve. So if I had to take the area under the curve, so this is going to be my area under the curve, but then I wouldn't know where to stop because this is unbounded. P2 is really somewhere, it is, all I can say is that the next limit is P2, which is infinity. So this is what kind of physically means. It's an improper integral. So, okay, so that's what we basically use now. During, or now the point is, it can get a little scary. You're like, okay, fine, you showed us some real complex equations, and then you came up with an even more, weird sort of thing, and you're calling this a solution. Now, how am I going to even, do this? How am I even going to, use this at all? Well, the interesting thing is that, all of these things, they actually reduce to, very nice formulae from here, right? So we don't have to worry about all this complex math, However, at the time when we're learning the subject, it's important to understand that, what goes in, to make something as comprehensive as this. But finally, when it comes to applying it, you will be using formulae to do that. So I will give you briefly, these formulae, although you can find this I got this from the book of Schlichting, so the reference is there, you can get that. Let me just give you a couple of, examples for this. I'm not going to, write all of this down, but okay. So this is the kind of formula that you can land up with, okay. This is the formula you can generate, okay. Now, for example, flat plate at 0 incidence, okay. Now, flat plate at 0 incidence right. So, wall shear stress is given by this formula, or for say a stagnation point flow, if I have a stagnation point flow, right. So, there my wall shear stress is given by this. Okay. Now, let me give you some these formulae. So, from here basically, you can, if I were to just give you, actually I won't be writing out all, but some actually. Okay. Now, so this is for the two cases, for the limiting cases. Here Prandtl number goes to, is very small, and here Prandtl number is very large. Okay. Now, there are, so these formula basically for specific cases. Okay. So, we have this, for example, for flat plate. Okay. Okay, it's a numerical solution, so you need boundary conditions. So, one boundary condition is where T W is equal to constant. So, this is more like the Dirichlet condition that I was talking to you about. Okay. So, then the solution here for this, the Prandtl number this case, is basically given like this. The Nusselt number by this, you get a nice little, pretty little formula. Nothing complicated, just pick this up and just use it. That's it. Okay. So, that, and then if it is very large, then what you get is this. Okay. That this is the cubic root of the Prandtl number, or if this is more difficult to understand, best to write this as Prandtl number raised to the power 1 by 3 by square root of x by L. Okay, so that's like one of these. Okay, so then the next one, okay, the next one is for the Neumann condition, where the heat flux is given, that's constant, right. So, basically the gradient of the temperature. Okay. So, then here again, so here again the same thing, right, that is equal to half, okay, by L. okay, and this, okay, is 0.464 Prandtl number raised to 1 by 3 by L. Okay, so that's one. So I've got two, okay, I've got a stagnation point and I got heated wall jet, okay, for both these conditions. So I could, give you those as well. So basically the point is, so, okay, I'm going to, not go further, not write any more formulae. You can actually pick this up. I'm writing this only for the flat plate, just to give you an idea that what it kind of reduces to. So you get similar formulae, okay, you have similar formulae for this, and the heated wall jet and things like that. So basically that's what it kind of reduces to, and you should be able to use these formulae to solve the problem. So what I'm trying to say is that this kind of usable formulae, something that we can trust, is something that you can come up after a lot of research and thought behind it. So that's what the objective was, to kind of give you a little insight into what went behind all of this research and understanding, so that we can come out with formulae like this, and and then we should be able to solve our real life problems with this. Okay, so I think we will stop here, okay, and I think we will be talking about the dissipation, the effects of dissipation in the next couple of modules. So I think I will stop here for now. So thanks.